A quick thanks to Squarespace for sponsoring this video. What if I told you that your entire life, everything you've ever seen, everyone you've ever met, every cluster of galaxies, stars, our planet, only makes up for less than 5% of the entire universe? The other 95+% is made of stuff that we physically cannot observe. Matter and energy which we do not comprehend. This has led scientists onto one profound quest of trying to improve our understanding of what all these mystical universal ingredients might be. According to Sir Isaac Newton, bodies have a mutual force on each other that is determined by their masses. The greater the mass, the greater the force. In addition, a large body's force on smaller, orbiting bodies greatly decreases over distance. During the 1930s, the Swiss-American astrophysicist Fritz Zwicky investigated the movements of galaxies within a huge galaxy cluster named Coma, about 300 million light-years away from Earth. Coma consists of thousands of galaxies orbiting around the center of the cluster in all possible directions, much like bees swarming around a beehive. By studying the movements of a few dozen galaxies to study the gravitational field that holds the cluster together, Zwicky was able to conclude something that didn't make much sense. The galaxy cluster rotated so rapidly that the gravity from the stars and gases and everything in the cluster could not possibly hold itself together. It wasn't even close, actually. The value he obtained said there needed to be at least 400 times the amount of matter in the cluster just in order to keep things held together. The galaxies rotated faster than their escape velocity, the speed that causes a celestial body to leave its orbit. For example, if we could increase Earth's orbital speed by just 1.5 times its current speed, our planet would be thrown out of our orbit around the sun and leave the solar system for good. Based on the insanely fast speeds Zwicky observed, the cluster should dissolve quickly and leave only traces of its former existence, but today the cluster is more than 10 billion years old. The universe itself is only 13.8 billion years old. Therefore, Zwicky concluded that there must be much more gravity in the Coma cluster than what one could see, some sort of matter that we could not see. He went on and gave this missing matter a name. For the first time, the term dark matter was used, and thus, the most prolonged unresolved mystery in modern astrophysics was born. However, Fritz's work was unpolished. The term dark matter Zwicky was using didn't talk about the same type of dark matter that we know today. He knew there was something there, he just didn't know what. In the 1970s, American astronomer Vera Rubin began studying individual stars in individual galaxies. Think of our solar system. Because they're closer to the sun, which, by the way, accounts for over 99% of the mass in our solar system, planets like Mercury have a much shorter orbital period than planets like Saturn and Jupiter. Now, size this up to a galactic scale. You would imagine that, as you go further towards the edge of the galaxy, the stars at the edge would be moving slower than the ones near the center. Vera Rubin was studying this exact thing. Except, she discovered the exact opposite. Within each galaxy, normal matter like stars and planets that are further away from the center of the galaxy move at speeds greater than the ones near the center. This doesn't make much sense. As you got further and further from the galactic center, the speeds at which stars moved flattened out, when in fact they should have decreased. If they moved too fast, they'd be flung out of the galaxy and lost forever. Too slow, and they'd literally fall out of their orbits. But instead, the speed stayed relatively the same. But this shouldn't happen. From this discovery, the rabbit hole known as dark matter gained popularity across the world. Dark matter is a supposed kind of material that doesn't emit, reflect, or interact with any kind of electromagnetic radiation. Things such as light, X-rays, gamma rays, radio waves, and so on. The only way we've been able to figure out that dark matter might exist is through gravity. Gravity is the bandwidth, it's the link between normal matter and dark matter. This sort of introverted matter is the reason why it's nearly impossible to detect. More direct evidence of the strange nature of dark matter lies in the amounts of hydrogen and helium there is in the universe. The nuclear fusion in the first few minutes after the Big Bang left round numbers, like 10 hydrogen nuclei for each one helium nucleus. Calculations show that, if most of the dark matter had participated in nuclear fusion, there would be much more helium in relation to hydrogen in the universe. From this, we can conclude that most of the dark matter, that is, most of the mass in the universe, does not participate in any fusion processes. This disqualifies it as ordinary matter, which very meaning lies in the willingness to interact with the atomic and nuclear power that builds up you and I. You might be able to say that dark matter and fusion processes just don't go together. According to Einstein, heavy objects can alter the geometry of spacetime. Instead of seeing gravity as a result of mass attracting mass, as Newton did, Einstein suggested that space and time bend around objects with mass. Imagine the universe as a flat grid, and objects with mass create a well of sorts in this grid. Objects with more mass, like stars and black holes, create a larger well that has a larger effect on matter around it. Everything follows the curvature of spacetime, light included. But something else that also bends light are lenses. If we were to imagine a cluster of galaxies, its gravitational pull literally would bend light around itself due to the sheer mass of the galaxy cluster. It creates a huge gravitational well. We can figure out the mass of the galaxy cluster based on how much light from the galaxy is being bent. This is called gravitational lensing. Scientists use this trick to determine the mass of two colliding galaxy clusters, called the Bullet Cluster, about 3.5 billion light years away. When clusters of galaxies collide into each other, they continue to travel. There isn't really even much of a crash. When the Milky Way collides with Andromeda in about 4 billion years, our solar system should remain unscathed. The sheer amount of literal space between stars is so massive that very few stars or planets will collide with one another. However, the gas in between the galaxies collides and is visibly noticeable. This is what happened here. The intergalactic gas inside the clusters collided with each other. They heated up and emitted X-rays that we can observe.